Okay, those are the formulas. You'll get all of those on the test, plus a couple more that I'll give you today. Those will be the basic formulas for the Laplace transform. If I think you need anything else, I'll give you other stuff too. So I'm going to leave those on the board all period. The basic test for today is to see how Laplace transforms are used to solve linear differential equations with constant coefficients. Now to do that, we're going to have to take the Laplace transform of a derivative. And in order to make sense of that procedure, we're going to have to ask, I apologize in advance, but a slightly theoretical question, namely, we have to have some guarantee in advance that the Laplace transform is going to exist. Now, how could the Laplace transform fail to exist? Can't I always calculate this? And the answer is no, you can't always calculate it, because this is an improper integral. I'm integrating all the way up to infinity, and you know that improper integrals don't always converge. You know, if the integrand, for example, were just didn't have the exponential factor there, was simply t dt, that it might look like it made sense, but that integral doesn't converge, and it's infinity, or anyway, it has no value. So I need conditions in advance which guarantee that the Laplace transforms will exist. Only under those circumstances will the formulas make any sense. Now, there is a standard condition, it's in your book, but I didn't get a chance to talk about it last time, so I thought I'd better spend the first few minutes today talking about that condition because it's what we're going to need in order to be able to solve differential equations. The condition that makes the Laplace transform definitely exist for a function is that f of t shouldn't grow too rapidly. It can grow rapidly because it can grow because the e to the minus st is pulling it down, trying hard to pull it down to 0 to make the integral converge. All we have to do is to guarantee that it doesn't grow so rapidly that the e to the minus st is powerless to pull it down. Now the condition is, it's a growth, what's called a growth condition. These are very important in applications, and this is the most, unfortunately, it's always taught in 1801, but it's not always taught in high school calculus. And it's a question of how fast the function is allowed to grow. And the condition is universally said this way, should be of exponential type. So what I'm defining is the phrase exponential type. I'll put it in quotation marks for that reason. What does this mean? It's a condition, a growth condition on a function. It says how fast it can get big. It says that f of t in size, since f of t might get negatively very large, and that would make the integral hard to converge, not likely to converge, I'll use the absolute value. In other words, I don't care if f of t is going up or going down very low. Whichever way it goes, its size should not be bigger than a rapidly growing exponential. And here's a rapidly growing exponential. So c is some positive constant. For some positive constant c and some positive constant k. And this should be true for all values of t. All t greater than or equal to 0. I don't have to worry about negative values of t because the integral doesn't care about them. I'm only doing the integration as t runs from 0 to infinity. In other words, f of t could have been an extremely wild function, sown a lot of oats or whatever functions do, for negative values of t, and we don't care. It's only what's happening from time 0 on to infinity. As long as it behaves now, from now on, it's okay. All right, so the way it should behave is by being of exponential type. Now, to try to give you some feeling for what this means, these functions, for example, if k is 100, Have any idea what the plot of e to the 100t looks like? It goes straight up. On every computer you try to plot it on, e to the 100t goes like that. Unless, of course, you make the scale t equals 0, 2, and over here is 1 billionth. Well, even that won't do. Okay, so these functions really can grow quite rapidly. Let's take an example and see what's of exponential type, and then perhaps even more interestingly, what isn't. So, for instance, the function sine t. Is that of exponential type? Well, sure. Its absolute value is always less than or equal to 1. So it falls in this paradigm if I take c equal to 1. And what should I take k to be? 0. Take k to be 0, c equals 1. In fact, sine t obeys that condition. Here's one that's more interesting. T to the n. Think of t to the 100th power. Is that smaller than some exponential with maybe a constant out front? Well, t to the 100th power goes straight up also. Well, we feel that if we make the exponential big enough, maybe it will win out. In fact, you don't have to make the exponential big. K equals 1 is good enough. In other words, I say I don't have to put absolute value signs around the t to the n because I'm only thinking about t as being a positive number anyway. I say that that's less than or equal to some constant m, positive constant m times e to the t will be good enough for some m. And all t. Now, why is that? Why is that? The way to think of that, so what this proves is that therefore t to the n is of exponential type, which we could have guessed because after all we were able to calculate its Laplace transform. Now, just because you can calculate the Laplace transform doesn't mean it's of exponential type, but in practical matters it almost always does. So t to the n is of exponential type. How would you prove that? Well, the way to the secret is to look at t to the n divided by e to the negative, e to the t. In other words, look at the quotient. What I'd like to argue is that this is bounded by some number, capital M. That's the question I'm asking. Now, why is this so? Well, I think I can convince you of it without having to work very hard. What does the graph of this function look like? It starts here, so I'm graphing this function, this ratio. When t is equal to 0, its value is 0, right? Because of the numerator. What happens as t goes to infinity? What happens to this? What does it approach? 0. And why? By lop. By L'Hopital's rule. Just differentiate, keep differentiating, reapply the rule over and over, keep differentiating it n times, and finally you'll have worn the numerator down to t to the 0, which isn't doing anything much. And the denominator, no matter how many times you differentiate it, it's still t to the t all the time. So by using L'Hopital's rule n times, you change the top to 1 or n factorial, actually. The bottom stays e to the t, and the ratio clearly approaches 0. And therefore, it approaches 0 to start with. So I don't know what this function is doing in between. It's a positive function. It's continuous because the top and bottom are continuous, and the bottom is never 0. So it's a continuous function which starts out at 0, is positive, and as t goes to infinity, it gets closer and closer to the t-axis again. Well, what can it do? You know, it might wave around. It doesn't actually. But the point is, because it's continuous, starts at 0, ends at 0, it's bounded. It has a maximum somewhere. And that maximum is m. So it has a maximum. All you have to know is where it starts and where it ends up, and the fact that it's continuous, that guarantees that it has a maximum. So, it is less than some maximum, and that shows that it's of exponential type. Now, of course, before you get the idea that everything's of exponential type, let's see what isn't. I'll give you two functions that are not of exponential type for different reasons. 1 over t is not of exponential type. Well, of course, it's not defined at t equals 0, but you know, it's okay for an integral not to be defined at one point because you're measuring area, and when you measure area, what happens at one point doesn't really matter much. That's not the thing. What's wrong with 1 over t is that the integral doesn't converge at 0. Times 1 over t dt. That integral, when t is near 0, this is approximately equal to 1, right? If t is 0, this is 1. So it's like the function integral from 0 to infinity of 1 over t. Near 0, it's close to, it's like the integral from 0 to some place of no importance, dt over t, but this does not converge. This is like log t, and log 0 is minus infinity, so it doesn't converge. So 1 over t is not of exponential type. So what's the Laplace transform of 1 over t? It doesn't have a Laplace transform. Well, what if I put t equals negative n? What about t to the minus 1? Well, that only works for positive integers, not negative integers. Okay, so it's not of exponential type. However, that's because it never really gets started properly. It's more fun to look at a function which is not of exponential type because it grows too fast. Now, what's a function that grows faster than... It grows so rapidly that you can't find any function e to the kt which bounds it. A function which grows too rapidly is, a simple one is, e to the t squared grows too rapidly to be of exponential type. And the argument is simple. No matter what you propose, it's always got, for the k, no matter how big a number, use Avogadro's number, use anything you want, ultimately this is going to be bigger than kt no matter how big k is. No matter how big k is. When is this going to happen? This will happen if t squared is bigger than kt. In other words, as soon as t becomes bigger than k, you might have to wait quite a while for that to happen. But as soon as t gets bigger than 10 to the 10 to the 23rd, this e to the t squared will be bigger than e to the 10 to the 10 to the 23rd times t. So e to the t squared, it's a simple function, a simple elementary function. It grows so rapidly, it doesn't have a Laplace transform. Okay, so how are we going to solve differential equations if e to the t squared? I won't give you any. And the reason I won't give you any, because I never saw one occur in real life. Nature likes sines, cosines, exponentials are fine. I've never seen a physical, you know, this is just my ignorance, but I've never seen a physical problem that involved a function growing as rapidly as e to the t squared. That's maybe just my ignorance. But I do know the Laplace transform won't be used to solve differential equations involving such a function. How about e to the minus t squared? That's different. It looks almost the same, but e to the minus t squared does this. It's very well behaved. That's the curve, of course, that you're all afraid of. Don't panic. Okay. So I'd like to explain to you now how differential equations, maybe I should save, tell you what, we need more formulas. So I'll put them, why don't I save this board, and instead I'll describe to you how the basic way differential Laplace transforms are used to solve differential equations. What do they call it? A paradigm. I'll show you the paradigm, and then we'll fill in the holes. So you have some overall view of how the procedure goes, and then you'll understand where the various pieces fit into it. I think you'll understand it better that way. So what do we do? Start with the differential equation, but right away there's a fundamental difference between what the Laplace transform does and what we've been doing up till now. Namely, what you have to start with is not merely a differential equation, let's say with linear with constant coefficients. It's almost never used to solve any other type of problem. And let's take second order so I don't have to do, because that's the kind we've been working with all term. But it's allowed to be inhomogeneous, so f of t. Oh, let's call this something else. I already ruined it. Another letter, h of t. I'll want f of t for the function, but I'm taking the Laplace transform up. All right. Now, the difference is that up to now you know how to techniques for solving this just as it stands. The Laplace transform does not know how to solve this just as it stands. The Laplace transform must have an initial value problem. In other words, you must supply from the beginning the initial conditions that the y is to satisfy. Now, I don't want to say any specific numbers, so I'll use generic numbers. Well, but look, what do we do? What do we do if we get a problem and there are no initial conditions? Does that mean we can't use the Laplace transform? No, of course you can use it, but you'll just have to assume the initial conditions are unknown numbers. You'll say, let the initial conditions be y sub 0 and y0 prime, or whatever you want to, a and b, whatever you want to call it. And now the answer then will involve the a and the b, or the y0 and the y0 prime. But you must at least give lip service to the initial conditions, whereas before we didn't have to do that. Now, depending on your point of view, that's a grave defect, or it's so what. Let's adopt the so what point of view. So there's our problem. It's an initial value problem. How is it solved by the Laplace transform? Well, the idea is you take the Laplace transform of this differential equation and the initial conditions. So I'm going to explain to you how to do that. Not right now, because we're going to need first the Laplace transform of a derivative, the formula for that. And you don't know that yet. But when you do know it, you'll be able to take the Laplace transform of the initial value problem. So I'll put the little L here. And what comes out is, well, y of t is the solution to the original problem. It's y of t is the function which satisfies that equation and these initial conditions. Its Laplace transform, let's call it capital Y, that's our standard notation, but it's going to be of a new variable s. So when I take the Laplace transform of the differential equation with the initial conditions, what comes out is an algebraic, the emphasis is on algebraic. No derivatives, no transcendental functions, nothing like that in it. An algebraic equation in y of s. And now what? Well, now, in the domain of S, it's easy to solve this algebraic equation. Not all algebraic equations are easy to solve for the capital Y, but the ones you will get will always be, not because I am making life easy for you, but that's the way the Laplace transform works. So you'll solve it for Y, and the answer will always come out to be Y equals y of s equals some rational function of s, some quotient of polynomials in s. A polynomial in s divided by some other polynomial in s. And now what? Well, This is the Laplace transform of the answer. This is the Laplace transform of the solution we're looking for. So the final step is to go backwards by taking the inverse Laplace transform of this guy. And what will you get? Well, you'll get y equals the y of t that we're looking for. It's really a wildly improbable procedure. In other words, instead of going from here to here, you have to imagine there's a mountain here, and the only way to get around it is to go first here, and then cross the stream here, and then go back up, and go back up. It looks like a senseless procedure, you know, what do they call it? Going around Robin Hood's barn, it was called when I was I don't know why it's called that, but that's what we used to call it. Not Laplace transform, that was just a generic thing when you had to do something like this. But the answer is that it's hard to go from here to here, but trivial to go from here to here. This solution step is the easiest step of all. This is not very hard. It's easy, in fact. This is easy and straightforward. This is trivial, essentially. Yeah, trivial. But this step is the hard step. This is where you have to use partial fractions, look up things in the table, and to get back there. So that most of the work of the procedure isn't going from here to here. Going from here to there is a breeze. Okay, now, in order to implement this, what is it we have to do? Well, the basic thing is I have to explain to you. You already know at least a little bit, a reasonable amount of technique for taking that step if you went to recitation yesterday and practiced a little bit. This part, I assure you, is nothing. So all I have to do now is explain to you how to take the Laplace transform of the differential equation. And that really means, how do you take the Laplace transform of a derivative? So that's our problem. What I want is, in other words, is a formula for the Laplace transform of f prime of t. Now, in terms of what? Well, since f is an arbitrary function, the only thing I could hope for is somehow to express the Laplace transform of the derivative in terms of the Laplace transform of the original function. So that's what I'm aiming for. Okay, where are we going to start? Well, starting is easy because we know nothing. If you don't know anything, then there's no place to start but the definition. Since I know nothing whatever about the function f of t, and I want to calculate the Laplace transform of its derivative, I better start with the definition. So whatever this is, it's the integral from 0 to infinity of e to the minus st times f prime of t dt. Now, what am I looking for? I'm looking for somehow to transform this so that what appears here is not f prime of t, which I'm clueless about, but f of t. Because if this were f of t, this expression would be the Laplace transform of f of t, and I'm assuming I know that. So the question is, how do I take this and somehow do something clever to it that turns this into f of t instead of f prime of t? Now, to phrase the question that way, I hope I would get 100% response on what to do, but I'll go for a 1%. So what should I do? I want to change that so that instead of f prime of t, f of t appears there instead. What should I do? Integrate by parts. The most fundamental procedure in advanced analysis. Everything important and interesting depends on integration by parts. And when you consider that integration by parts is nothing more than just the formula for the derivative of a product read backwards, it's amazing. It never fails to amaze me, but it's okay. That's why mathematics is so great. Okay, so let's use integration by parts. Integration by parts. Okay, so we have to decide, of course, there's no doubt that this is the factor we want to integrate, which means we have to be willing to differentiate this factor. But that'll be okay because it looks practically like any exponential. It looks practically the same after you've differentiated it. So let's do the work. The first step is you don't do the differentiation. You only do the integration. So the first step is e to the negative st, and the integral of f prime of t is just f of t. And that's to be evaluated between the limits 0 and infinity. And then minus, again, before you forget it, put down that minus sign, the integral between the limits of what you get by doing both operations, both the differentiation and the integration. So the differentiation will be by using the chain rule. Remember, I'm differentiating with respect to t. The variable is t here, not s. S is just a parameter. It's just a constant, a variable constant, if you get my meaning. That's not an oxymoron. A variable constant. A parameter is a variable constant. A variable because you can manipulate the little slider and make it change its value, right? That's why it's variable. It's not a variable. It's variable. You get the distinction. Okay. Well, I mean, it becomes a variable, but it's but right now it's not a variable. It's just sitting there in the integral. All right. So minus s e to the negative st f of t dt. Now, this part's easy. The interesting thing is this expression. So, and the most interesting thing is I have to evaluate it at infinity. Now, of course, that means take the limit as you go toward, as you let t goes to infinity. Now, what I'm interested in knowing is what's the limit of that expression. I'll write it as f of t divided by e to the st. Remember, s is a positive number. As t goes to infinity, and I want to know what the limit of that is. Well, the limit is what it is, but really, if that limit isn't 0, I'm in deep trouble since the whole process is out of control. What will make that limit 0? Well, that f of t should not grow faster than e to the s of t if s is a big enough number. And now that's just what will happen if f of t is of exponential type. It's for this step right here is the most critical place at which we need to know that f of t is of exponential type. So that limit is 0 since f of t is of exponential type. In other words, that the value, the absolute value of f of t becomes less than, let's say, put in the c if you want, but it's not very important, c e to the kt, for all values of t, and therefore this will go to 0 as soon as s becomes bigger than that k. In other words, if f of t isn't growing any faster than e to the kt, then as soon as s is a number, that parameter has a value bigger than k, this ratio is going to go to 0 because the denominator will always be bigger than the numerator and getting bigger faster. So this goes to 0 if s is bigger than k. And so at the upper limit, therefore, this is 0, again, assuming that s is bigger than that k, the k of the exponential type. How about at the lower limit? We're used to seeing 0 there, but we're not going to get 0. If I plug in t equals 0, this factor becomes 1. And what happens to that one? F of 0. You mean I'm going to have to know what f of 0 is before I can take the Laplace transform of this derivative? The answer is yes. And that's why you have to have an initial value problem. You have to know in advance what the value of the function that you're looking for is at 0 because it enters into the formula. I didn't make up these rules. I'm just following them. So what's the rest? The two negatives cancel, and you get plus s. It's just a parameter, so I can pull it out of the integral. I'm integrating with respect to t. And what's left is, well, what is left? If I take out minus s, combine it there, I get what's left is just the Laplace transform of the function I started with. So it's f of s. And that's the magic formula for the Laplace transform of derivative. So it's worth putting up in our little list. So f prime of t, assuming it's of exponential type, has as its Laplace transform, well, what is it? It's, let's put down the major part of it is s times whatever the Laplace transform of the original function f of t was. So I take the original Laplace transform, I multiply it by s. That corresponds to taking the derivative. But there's also that little extra piece. I must know the value, the starting value of the function. And this is the formula you will use to take the Laplace transform of the differential equation. Now, but you see, I'm not done yet because that'll take care of the term ay prime, but I don't know what the Laplace transform of the second derivative is. Okay. So we need a formula for the Laplace transform of the second derivative as well as the first. Now, the hack method is to say, second derivative, all right. I know how to do this, so second derivative here, second derivative here, gulp, what do I do with that? Aha, I integrate by parts twice. Yes, you can do that, but that's a hack method, and of course I know you're all too smart to do that. What you would do instead is okay, how are we going to fill that in? Well, a second derivative is also a first derivative. A second derivative is the first derivative of the first derivative. Okay, now we'll just call this glop. Something. So it's glop prime. And what is the formula for the Laplace transform of glop prime? It is, well, I have my formula. It is the glop prime, the formula for it is the S times the Laplace transform of glop, okay? Glop, well, glop is f prime of t. I'm not done yet. Minus glop evaluated at 0. What's glop evaluated at 0? Well, f prime of 0. Now, I don't want the formula in that form, but I don't have to have it in that form because I know what the Laplace transform of f prime of t is. I just calculated that. So this is equal to s times the Laplace transform of f prime of t, which is s times f of s, capital F of s, minus f of 0. All that bracket stuff corresponds to this guy. And don't forget the stuff that's tagging along, minus f prime of 0. And now put that all together. What is it going to be? Well, there's the principal term, which consists of s squared multiplied by f of s. That's the main part of it. And the rest is the sort of fellow travelers. So we have minus s times f of 0, little term tagging along. This is a constant times s. And then we got another one, still another constant. So what we have is, to calculate the Laplace transform of the second derivative, I need to know both f of 0 and f prime of 0, exactly the initial conditions that the problem was given for the initial value problem. But notice, there's a principal part of it. That's the s squared f of s. That's the guts of it, so to speak. The rest of it, you might hope that these two numbers are 0. It could happen, and often is made to happen in problems to simplify them. In that case, you don't have to worry. They're not there. But if they are there, you must put them in or you get the wrong answer. So that's the list of formulas. So those formulas on the top board and these two extra ones, those are the things you'll be working with on Friday. But I stretch, the Laplace transform won't be a big part of the exam. The exam, of course, doesn't exist. But let's say a maximum of, I don't know, 20%? Maximum of 20%. Maybe 15, I don't know. 20%, 50. Give or take a few points. Yeah, what's a point or two? Okay, let's solve. We have time. Yeah, we got time to solve a problem. Let's solve a problem. Problem. See, I can't touch that. I can't. Untouchable. 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 All right. Okay, this we got to keep. Problem. Okay. Okay. Now, you know how to solve this problem by operators. Let me just briefly remind you of the steps, the basic steps. You have to do two separate tasks. You have to first you have to solve the homogeneous equation, putting a 0 there. That's the first thing you learn to do. That's easy. You could almost do that in your head now. You get the characteristic polynomial, get its roots, get the two functions, e to the t and e to the negative t, which are the solutions. You make up c1 times 1 plus c2 times the other. That's the complementary function, solves the homogeneous problem. And then you have to find a particular solution. Can you see what would happen if you try to find the particular solution? The number here is -1, right? -1 is a root of the characteristic polynomial. So you got to use that extra formula. It's okay. That's why I gave it to you. You use the exponential input theorem with the extra formula, and then you'll get the particular solution. And now you have to make the general solution. Particular solution plus the complementary function. And now you are ready to put in the initial conditions. At the very end, when you got the whole general solution, now you put in, and not before, you put in the initial conditions. You have to calculate the derivative of that thing to substitute this. You take it as it stands to substitute this. You get a pair of simultaneous equations for C1 and C2. You solve them. Answer. It's a rather elaborate procedure which has at least 3 or 4 separate steps, all of which, of course, must be done correctly. Now, the Laplace transform instead feeds the entire problem into the Laplace transform machine. You follow that little blue pattern, and you come out with the answer. So let's do the Laplace transform way. Okay. So the first step is to say, here's my unknown function y of t. It obeys this law, and here are its starting values of it and its derivative. What I'm going to take is the Laplace transform of this equation. In other words, I'll take the Laplace transform of this side and this side also, and they must be equal, because if they were equal to start with, the Laplace transforms also have to be equal. Okay, so let's take the Laplace transform of this equation. Okay, first I need the Laplace transform of the second derivative. Okay, that's going to be, don't forget the principal terms. There's some people, who get so hypnotized by this. I just know I'm going to forget this. So they write there that they forget this, but that's everything. That's the important part. Okay, so it's S times, I'm calling the Laplace transform not capital F, but capital Y, because my original function is called little y. So it's S squared y, it's y of S, but I'm not going to put the S of S in because it just makes the thing look more complicated. And now before you forget, you have to put in the rest. So minus S times the value at 0, which is 1, minus the value of the derivative, but that's 0, so this is not too hard a problem. So minus s minus 0, so I don't have to put that in. So all this is the Laplace transform of y double prime. And now minus the Laplace transform of y, well, that's just capital Y. What's that equal to? The Laplace transform of the right-hand side. Okay, look up the formula. It is e to the negative t. A is minus 1, so it's 1 over s minus minus 1. So it is s plus 1. This is that. Okay, the next thing we have to do is solve for y. That doesn't look too hard. Solve it for y. Okay, the best thing to do is put s squared, group all the y terms together unless you're really quite a good calculator. Maybe make one extra line out of it. Yeah, definitely do this. And then the extra garbage, I refer to as the garbage, this stuff, and this stuff. The linear polynomials which are tagging along, move to the right-hand side because they don't involve capital Y. So this will move to the other side. And so that's equal to 1 over s plus 1 plus s. Now you have a basic choice. About half the time, it's a good idea to combine these terms. The other half the time, it's not a good idea to combine those terms. So how do we know whether to do it or not to do it? Experience, which you will get by solving many, many problems. Okay. I'm going to combine them because I think it's a good thing to do here. So what is that? That's s squared plus s plus 1. So it's s squared plus s plus 1 divided by s plus 1. Okay? I'm still not done because now we have to know what's y. All right, now you have to think. What we're going to do is get y in this form, but I want it in the form in which it's most suited for using partial fractions. In other words, I want the denominator as factored as it possibly can be. Okay, well, the numerator is going to be just what it was. How should I write the denominator? Well, the denominator is going to have the factor s plus 1 in it from here. But after I divide through, the other factor will be s squared minus 1, right? But s squared minus 1 is s minus 1 times s plus 1. So I have to divide this by s squared minus 1. Factored, it's this. So the end result is there are 2 of these and 1 of the other. And now it's ready to be used. It's ready to be partial fraction. So the final step is to use a partial fractions decomposition on this so that you can calculate its inverse Laplace transform. So let's do that. Okay. S squared plus s plus 1 divided by that thing, s plus 1 squared times s minus 1 equals s plus 1 squared plus s plus 1 plus s minus 1. In the top will be constants, just constants. Let me let's do it this way first, and I'll say at the very end something else. Maybe now. Many of you are upset. Some of you are upset. I know this for a fact. Because in high school or wherever you learned to do this before, there weren't 2 terms here. There was just 1 term, s plus 1 squared. If you do it that way, then it's all right, but I don't recommend it. In that case, the numerators will not be constants, but if you just have that, then because this is a quadratic polynomial all by itself, you've got to have a linear polynomial, as plus b in top. You see? So you must have as plus b here, as I'm sure you remember, if that's the way you learned to do it. But to do cover-up, the best way, as much as possible, the best way is to separate out the terms. If this were a cubic term, God forbid, s plus 1 cubed, then you'd have to have s plus 1 cubed, s plus 1 squared, s plus 1. Okay, I won't give you anything bigger than quadratic. You can trust me. Okay, now what can we find by the cover-up method? Well, surely this. Cover up the s minus 1, put s equal 1, and I get 3 divided by 2 squared, 4. So this is 3/4. Now, in this, you can always find the highest power by cover-up. Because cover it up, put s equal negative 1, and you get 1 minus 1 plus 1. So 1 up there, negative 1 here makes negative 2. So it's 1 over negative 2, so it's minus 1/2. Now this you cannot determine by cover-up, because you'd want to cover up just one of these s plus 1s, but then you can't put s equal negative 1 because you get infinity. You get 0 there, makes infinity. So this must be determined some other way, either by undetermined coefficients, or if you've just got one thing, for heaven's sake, just make a substitution. See, this is supposed to be true. This is an algebraic identity, true for all values of the variable, and therefore it ought to be true when s equals 0, for instance. Why 0? Well, because I haven't used it yet. I used negative 1 and positive 1, but I didn't use 0. Okay, let's use 0. Put s equals 0. What do we get? Well, on the left-hand side, I get 1 divided by 1 squared negative. So I get minus 1 on the left-hand side equals, what do I get on the right? Put s equals 0, you get negative 1/2. Well, this is the number I'm trying to find. So let's write that simply as plus c, putting s equals 0. S equals 0 here gives me negative 3/4. Okay, what's c? This is minus 1/2 minus 3/4 is minus 5/4. Put it on the other side. Minus 1 plus 5/4 is plus 1/4. So c equals 1/4. And now we're ready to do the final step, take the inverse Laplace transform. You see what I said when I said that all the work is in this last step? Just look how much of the work, how much of the board is devoted to the first two steps and how much is going to be devoted to the last step. Okay, so we need the inverse Laplace transform. Well, the first term is the hardest. Let's let that go for the moment. So leave a space for it. And then we'll have 1/4. Well, 1 over s plus 1 is, that's just the e exponential formula. 1 over s plus 1 would be e to the negative t. E to the minus 1 times t. So it's 1/4 e to the minus 1 times t. And how about the next thing would be 3/4 times, well, here it's negative 1, so that's e to the plus t. Notice how those signs work. And that just leaves us the Laplace transform of this thing. Now, you look at it and you say, this Laplace transform happened in 2 steps. I took something and I got essentially 1 over s squared, and then I changed s to s plus 1. All right. What gives 1 over s squared? The Laplace transform of what is 1 over s squared? T. You say to yourself, 1 over s to some power is essentially some power of t, and then you look at the formula. Notice the top is 1 factorial, which is 1, of course. Okay, now then, how do I convert this to 1 over s plus 1 squared? That's the exponential shift formula. If you know what the Laplace, so the first formula in the middle of the board on the top there, if you know what, you change s to s plus 1, corresponds to multiplying by e to the t. So it is t times e to the negative t, sorry, that corresponds to this. So this is the exponential shift formula. If t goes to 1 over s squared, then t e to the minus t goes to 1 over s plus 1 squared. Okay, but there's a constant out front, so it's minus 1/2 t e to the negative t. Now, tell me, what parts of this solution, oh boy, we're over time, but notice, this is what would have been the particular solution, yp before, and this is the stuff that occurs in the complementary function, but already the appropriate constants have been supplied for the coefficients. You don't have to calculate them separately. They were built into the method. Okay, good luck on Friday, and see you there.